So we are group 6, and this is our progress. A brief summary on our paper. The study is describing the free surface region using the Conn-Hilliard-Navier-Stokes model, and this is used to optimize ship shapes to reduce drag.
So for this experiment, we wanted to simulate a submerged hydrofoil. Our goal was to simulate wave patterns downstream of a hydrofoil as it's moving through water. The assumptions will be it's going to be on a 2D domain. It's going to have a fixed inlet velocity. It's going to be fully developed at the inlet velocity and steady state. Using this information, we were able to simplify the Navier-Stokes governing equations to this equation right here. The boundary condition for our simulation includes 6 key boundary zones. The first will be the inlet velocity that's going to be at a fixed velocity. The second boundary will be the outlet that's going to have a fixed hydrostatic pressure. The third and fourth will be the upper and lower boundaries that's going to be at a slip condition following this equation. The fifth is the interaction layer between the water and the air using the continuity equation. And lastly, the sixth boundary is the non-slip surface around the hydrofoil interacting with the water. Lastly, using this put into MATLAB, we were able to simulate a basic pressure gradient as the flow moving from the left side of the screen. As you can see, producing a higher pressure on top of the hydrofoil and causing those wave interactions with the air. As you move farther downstream, the water settles down and becomes laminar again.
So for the ANSYS setup, we were actually given a domain in the paper, and it's going to be 75 by 25 control volume multiplied by the chord length of the hydrofoil. So we actually chose a 100 millimeter chord length with a 5-degree angle of attack. And for the laminar model specifically, the assumptions I made were that it was steady state, incompressible, fully developed, and again laminar. And due to the laminar nature, I assume that the only source of velocity is going to be the velocity of the wave at 1.1 meters per second, and that the hydrofoil is stationary in the water. For the two-phase flow, I would just use the volume of fluid, and the pressure is going to be 1 atmosphere. So for the mesh, we had to separate it between air, water, and free surface. So for the 7,500 by 2,500 millimeter control volume, mine consisted of 63,181 nodes and 83,662 elements. And you can see on the right side the difference in mesh and size as it goes towards the hydrofoil. So for the results, you can see that for the laminar flow, the wave height break occurs at 700 millimeters downstream with a wave height of approximately 50 millimeters. And it's very small because due to the laminar nature of the flow. And then on the right side, you can see the velocity profile of the flow around the hydrofoil. And due to Navier-Stokes, you can see that the velocity flow increases at the start of the hydrofoil and then decreases at the back end of the hydrofoil. So I went ahead and calculated the lift force and drag coefficient as well as the hydrofoil. And as you can see, as it goes through the iterations, it increases and then decreases towards the end of the flow. ANSYS calculated the hydrofoil lift force at 18.36 newtons and then the drag coefficient at 3.17.
So I'm looking at the turbulent downwind volume of fluid for this analysis. What I'm looking at is the 100 millimeter with a 5 angle of attack hydrofoil. My mesh generates a 7,500 by 2,500 millimeter domain, and the mesh consists of a top portion, which is the air-free surface, which is the middle, and the bottom region, which is water. The results show the downwind effects of the submerged hydrofoil to the wave height. What we're looking at here is velocity of 6.1 meters per second, which is considered the average ship velocity. Under the K omega turbulence model and two-phase flow on ANSYS for steady state conditions, we analyze the turbulent downwind effects. From the graphic we see, and from measurements taken, we see that the wave height is a volume fraction of 1 as depicted. 50 millimeters past the leading edge of the hydrofoil, the wave height is decreased by 10 millimeters, with turbulent mixing 20 millimeters upwind of the hydrofoil. At 1,100 millimeters from the trailing edge, the free surface is stabilized, and we see generally small amounts of turbulent mixing throughout. Thanks.
Thank you. That's our progress.